When your personal laptop freezes, it's an annoyance. You lose an hour of work and restart. When an industrial computer freezes, a multi-ton robotic arm swinging at full speed drops its payload, destroying equipment and endangering lives. To prevent that, factories run on a completely different kind of machine, the Programmable Logic Controller, or PLC. It is the invisible, ultra-reliable computer powering high-stakes physical systems. Before PLCs, controlling a 1960s assembly line required massive cabinets stuffed with thousands of mechanical relays. If an engineer needed to change a production sequence, they had to spend weeks physically rewiring the entire wall. In 1968, Dick Morley solved that problem. He invented a single, ruggedized box that replaced the mechanical switches with programmable code. The PLC perfectly solved the hardware nightmare of 20th century manufacturing. But by becoming the universal standard, it inadvertently planted a massive, invisible vulnerability for the 21st century. Today, PLCs run 80% of global automation. They silently manage power grids, water treatment plants, and sprawling chemical refineries. That massive deployment makes them a prime target. We have already seen highly sophisticated, weaponized cyber attacks like Stuxnet and Triton, specifically designed to infiltrate these systems. These attacks ignore standard enterprise IT networks. They dive straight into the PLC to physically manipulate machinery and disable safety protocols. This introduces a paradox. If these controllers run our most vital, dangerous infrastructure, why can't we protect them with basic antivirus software or strong password protocols? Because the exact engineering traits that make a PLC indestructible on the factory floor are the exact same reasons it is defenseless on the open internet. This architecture diagram shows the three core physical components of a PLC: the input module, the processor, and the output module. Inputs translate physical conditions into digital data. The processor evaluates it, and outputs translate the commands back into physical action, like opening a valve. The machine runs one core loop called the scan cycle. It reads inputs, executes logic, and updates outputs, repeating thousands of times per second. This creates strict determinism. The PLC executes its routine continuously with mathematical precision, without background interruptions. That rigid determinism guarantees safety. There is no operating system looking for updates or running background apps to distract the processor from controlling dangerous machinery. Your personal laptop is a general-purpose machine. It constantly juggles different applications, searches for Wi-Fi, and downloads patches. PLCs prioritize speed and physical control above all else. They simply lack the computing overhead required to run heavy cryptographic encryption or complex authentication protocols. You also can't push standard IT updates to operational technology. Rebooting a controller for a security patch means completely halting a live power grid, or stopping a continuous flow of molten metal. Now we are connecting these unencrypted, unpatchable 1960s hardware architectures to modern cloud networks and the Internet of Things. That creates a frictionless entry point for hackers. Introducing standard IT security software directly onto a PLC would destroy the flawless, continuous uptime it was built to provide. Since we cannot alter the PLC's internal operations without compromising its performance, cybersecurity teams have to build fortresses around it. This starts with network segmentation, creating a strict, impenetrable barrier between the enterprise IT network and the factory floor. At that barrier, intrusion prevention systems act as virtual patches, intercepting malicious commands before they ever cross over to the controller. Modern industrial defense relies entirely on isolating the machine's environment rather than forcing the machine to defend itself. This best practices document highlights another defense: secure PLC coding. Engineers use the PLC's simple logic as a shield. By keeping strict operational rules explicitly inside a controller, the machine regulates itself. If a hacker injects abnormal data, the rigid program rejects it as illogical. Despite the escalating threat of cyber attacks, the PLC is not going anywhere. It will remain the foundational, indestructible brain of global industry. True industrial security doesn't mean changing what the PLC is. It means respecting its deterministic nature and changing how we build the connected world around it.